Hello, in this video I'm going to go over configurations for resistors and configurations for capacitors. So series and parallel configurations. So we will start with resistors. And then we're going to start with resistors in series. So for resistors in series, we want to be able to, for each of these configurations, simplify them into a single equivalent resistance or capacitance later on. So what that means is that when we have resistors in series, we start off with something that looks like this, where you have, in the most simple case, we can simplify two resistors into one, and then we can keep repeating that if we have more resistors in series. But in the most simple case, we have two resistors in series together. Let's say we'll have R1 and R2. And then there's going to be a voltage across both of them. So if we call this side ground, um, or this side 0 volts. So this symbol here, by the way, it's like this is the ground symbol, and this is basically just a 0 volt reference. So whenever you see this symbol, it just means that anything connected directly to it is at 0 volts. And then let's just say that the other side is at V. And then there's going to be a current, we'll call it current I, that flows through both of these resistors. And we want to turn these two resistors in series into a single equivalent resistance that will behave the same way. So what we want to do is um, turn these two resistors into a single resistance Req that will have the same current when the same voltage is applied through it. So using Ohm's law, we know that V equals IR. So we know from that, this side, we know that voltage here on this side is equal to, so this V here is going to be equal to um, I R1 plus IR2, because this, like, IR1 is the voltage across this first resistor and IR2 is the voltage across the second resistor, and they have to add up to the total voltage here. And so the voltage is going to be IR1 plus R2. And on this right side, we see that voltage here is equal to just IREQ. Now, remember that we said the voltage is the same because we want to just find an equivalent resistance that can replace these two resistors. So from that, we get that IR1 plus IR2 is equal to IREQ. And then since the current is also the same, since we already said that we wanted that to happen, we can cancel these currents out, and then we just get that R1 plus R2 is equal to REQ. So you see that whenever you have resistors in series, you can simply add them directly to get an equivalent resistance. And now this is only two, but what if we have multiple? Well, if we have, like, say, three resistors, we can combine two of them first and then combine one more. And then you can keep doing that, just one pair at a time for resistors until you reach a final equivalent resistance. But the process will also always be adding. So if you want to find an equivalent resistance for multiple resistors, the general formula would just be REQ. So the equivalent resistance is equal to the sum of the series resistances. So this is the general formula for series resistance, series resistors. Okay, so one way to get intuition for this, or an easy way to remember it, is remember the formula for calculating resistance for a given material is R resistance is equal to rho, which is the resistivity, times L, the length of the material, divided by A. Now, when you add resistors in series, you're adding them basically like end to end. So you're not increasing the cross-sectional area, but when you add them end to end like this, you can think of it as increasing the length. And since resistance is directly proportional to length, when you add the lengths together, you can think of it as directly adding the resistances together to get an equivalent resistance. Now, one useful application of this series configuration is a voltage divider. So, a voltage divider. A voltage divider will look something like this. So, typically see it like this, where there's two resistors in series, and then there's going to be one node coming out from in the middle of those two resistors. But this is just saying the potential between these two resistors, basically. So we have V in here. So this is the voltage that goes into the voltage divider. And then we have this side connected to ground, so 0 volts. And then this we will call V out. And then R1, R2. Now we want to find a formula for V out given V in, R1, and R2. So now we know that there's going to be a current through this. Let's call it just I here again. We know that the current I is going to be equal to V in divided by Req. And then since we determined that the equivalent resistance is just equal to the sum of the series resistances, we know that I is going to be equal to V in divided by R1 plus R2. Now, if we want to find the voltage drop across any resistor, we know that V out is going to be referenced to ground, so which means we want to find the voltage difference between this point and ground, which is the same as the voltage drop across R2. And now we know the voltage drop across R2 is just going to be I R2, right? And then this again is going to be equal to V out. So we already found I here, so we get the formula V out is just equal to V in times R2 over R1 plus R2. So this is a formula that you can use to get the output voltage for a voltage divider. Now a voltage divider doesn't necessarily have to look exactly like this, but it's just whenever you have two resistors in series, you can find the voltage between them by applying this formula. But the voltage drop across an individual resistor is just going to be so the resistance in the numerator here is the resistor you're trying to find the voltage drop across. So when you do a voltage divider like this is not the voltage drop of the first resistor. This is the voltage drop of the second resistor because it's referenced to ground. If you want to find the voltage across the first resistor, you're going to have to do V1. VR1 is equal to V in times R1 over R1 plus R2. So that's an important thing to remember. Okay, now we will go and cover parallel resistors. So these are parallel resistors. So before we looked at two resistors in series, and now we're going to look at two resistors in parallel. So that would look something like this. You just have two resistors in parallel. So this again will be ground. Let's call this V. And then there's going to be an overall current I that flows in this direction. And so this is R1 and R2. And we want to be able to find, like before here, we found a equivalent resistance like this. We want to be able to do that again. So we want to turn these two parallel resistors into a single equivalent resistance that behaves the same way. So again, there's going to be the same voltage across them, same current, overall current, but then there's going to be one resistor here. And then so this is Req. Again, we can apply Ohm's law. So we know that current here, the current across each of these branches is going to be, if we call this like I1 and then we call this I2, we know that I1 is going to be equal to V divided by R1 and I2 is equal to V divided by R2 by Ohm's law. And then we know that the total current I is going to be I1 plus I2 by Kirchhoff's current law. So the node, you can see that there's a node here, and the current entering and leaving the node have to sum to 0. And so this equation must be true. And so now we can plug that in and get I is equal to V over R1 plus V over R2. Now for this other side, the equivalent resistance side, is much easier. We get that the current I is going to be E over Req. So we can set these equal to each other and say that I here, so both of them are equal to I because they're equivalent. And now we get that V over R1 plus V over R2 is equal to V over Req. And we can cancel the V's out because the voltages are all equivalent again, because we want these to behave the same exact way. And so what we end up here is 1 over R1 plus 1 over R2 is equal to 1 over 1 over Req. And again, the general form is for that is we can combine any amount of parallel resistors 2 at a time like this. And so in doing that, we get the formula 1 over Req is equal to the sum of the parallel resistances. So this is the general formula for parallel resistor, or sorry, so this should be the reciprocal of parallel resistance. The sum of the reciprocals of the parallel resistances. So this is the general formula for combining parallel resistors. And again, as I said before, we saw that when you're adding series resistors together, you're adding them end to end. So you're adding the lengths, you can think of it. So that was why it's a direct relationship. But for parallel resistors, again, we have resistance is equal to rho L over A. When you add them side by side, you're not increasing the length, but you're actually increasing, you can think of it as increasing the cross-sectional area. Because if you take a cut through any of these two, like if you have two resistors in parallel like this, and then you take a cut through them, like to find the cross-sectional area, you have to add the areas together. So you have to add like the area from this resistor and the area from this resistor. So this is going to be related to the area, and you see that R is proportional to the inverse of area. And so that's how you can think of it, as like you're adding the inverses together. So the equivalent area is going to be the inverse, like again, so you have to deal with inverses since area is on the bottom of this fraction. And that's one way you can think about remembering it or gaining intuition if you forget. Now, before, when you had resistor in series, you had a voltage divider. But now the voltage is the same, but now current splits. So you can think of resistors in parallel as being a current divider. So let's analyze it as a current divider. So again, as we said before on top, we have, let's just say, voltage here, and then we have two resistors, R1 and R2, and then let's connect this side to ground. So this is ground. And then we have a total current I in, and then there's going to be I1 and I2 going through these. And then this is R1, R2. And now we want to be able to find I1 or I2 based on I in and R1 and R2. So how do we do that? Now, we know before, like I said, that we have this equation up here, which is, this is the same scenario. We have total current is equal to the sum of, sorry, there should be an I1 here. Total current is equal to the sum of I1 plus I2. And then the individual currents are equal to V over R1 and V over R2. So what we get here is that this total current I in is going to be equal to V times 1 over R1 plus 1 over R2. All right, and then if we find a common denominator and combine these, so simplify this these two fractions added together, we get that I in is going to be equal to V times R1 plus R2 over R1 R2. So these two are the same. And now what we can do is we can solve for V. So V is equal to I times R1 R2 over R1 plus R2. All right, now we want to solve for current 1 or current 2. So let's just say current 1 because current 2 will we can solve it the same way. We know that I1 here is equal to V divided by R1. And we have V here. So if we do V divided by R1, this is equal to I times R1, R2 over R1 plus R2 divided by R1. And then we see that these cancel out right now. So um, what we end up with is, this is I in, by the way. What we end up is I1 is equal to I in over times R2 over R1 plus R2. And so this is a formula for current divider, or like how the current is divided when it gets to this junction of resistors. So we see that the current I1 is going to be related to R2. So if R2 is greater than R1, then I1 is going to be greater than I2. And so you see that current is inversely proportional to resistance. And this makes sense because we have that voltage, which is the same, is equal to IR, right? So that means that current is going to be inversely proportional to resistance because voltage is constant, but these two have to multiply together to get a constant value. And then again, this formula is really similar to a voltage divider formula. But you just have to remember if you want to, it's really this equation, this relation that's important. So current is inversely proportional to resistance. And then from that, in Ohm's law, you can derive a current divider formula. Now we are going to move on to capacitor configuration. So capacitors in series and parallel. So first we can do capacitors in series. Again, I'll draw out what we're trying to achieve here. So we have two capacitors that look like this in series. And then we have a voltage here. Let's call this ground. And then we have current I flowing through here, or this is charging current. So this is when the capacitor is still charging. We have current I, let's say. And then this is C1 and C2. And we want this to be able to be represented by a single capacitor that behaves the same. So V, and then this is ground here. And then this is CEQ, and here we have I. So now notice that the current that flows through both of these is going to be I. So capacitor 1 has current I through it, and capacitor 2 has current I through it as well. And remember here that I, current, is equal to charge over time. Sorry, charge should be Q. Charge over time. Or if you want to write it in terms of if you want to write it in terms of like derivatives or infinitesimals, you can write current is equal to dq over dt. So this is charge over time. Now, if you see that the current going through each of these capacitors is the same, there's no need to write a current one here. The current going through each of these capacitors is the same, which means that, and since they're going to be charging over the same period of time too, because there's only one branch, then charge on these two capacitors is also the same. Because if you have current flowing through it, then these capacitors are getting charged, but then for a period of time. So they charge with the same current and the same period of time. So the charge on both of these capacitors has to be the same. And so we know that Q1 is equal to Q2. And then if we want these to behave the same, if it takes delta T to charge this side, it should take the same delta T to charge this end. And if it takes the same time with the same current, then we know that this charge EQ is also the same because there's the same current flowing through that for the same amount of time as these two. So this is a very important equation relationship here because we get that so well first we know that um, the capacitors follow the equation charge is equal to um, capacitance times voltage. And so we know that voltage here, well, and then voltage, so the voltage across each of these capacitors can be written as V1 is equal to Q1 over C1, and then V2 is equal to Q2 over C2. And then we know that the total voltage V is equal to V1 plus V2, which is equal to Q1 over C1 plus Q2 over C2. And on this other side, we get that the total voltage is equal to Q EQ over C EQ. And then now since these are equal, we can set them equal. So Q1 over C1 plus Q2 over C2 is equal to QEQ over CEQ. And since from this we know that the charges are all equal, we can cancel them out. And then we get our equation for two capacitors in series. The equivalent capacitance is C or 1 over C1 plus 1 over C2 is equal to 1 over CEQ. And so again, as I said before, this is for two, but if you want to do many of them, you can just keep adding the reciprocal capacitances together. So the overall formula for series capacitors is 1 over CEQ is equal to the sum of the individual reciprocals of the capacitors in series. So this is the general formula for capacitance or capacitors in series. And one way we can gain intuition by this is looking at the formula for capacitance. So we get that C is equal to K epsilon naught A over D. Now, if you're adding two capacitors in series, like this, you're not changing the area, cross-sectional area at any point, because if you take a slice through them, the areas will be the same as if you didn't add them. But if this is D1 and this is D2, then this new distance between them is going to be added together since you're combining them end to end. So we know that C is inversely proportional to distance. And so if you're adding them in series, you can think of them as adding the distances together, which is why you're dealing with reciprocals for capacitance. Now, like resistors in series, we can come up with a voltage divider formula for capacitors. So voltage divider. Again, we want to start with the same configuration. So V in on one side, and then you have two capacitors here, C1 and C2, and then ground on this other side. All right, so we have a V out here now. Now, we know that Q is equal to CV. And so we know that C1 V1, since the Q1 is equal to Q2, we know that C1 V1 is equal to C2 V2. And then since we're trying to find V out here, which is the difference between this point and ground, we know that V out is equal to V2. And if we solve for V2 in terms of this, we get that V2 is equal to V1 C1 over C2. All right, so we know that V2 is equal to C1 V1 or V1 C1 over C2. Um, and we also know that the sum of the voltages have to add to Vn. So Vn is equal to V1 plus V2. So we know that V2 is equal to Vn minus V1. So now if we substitute V1 in here, we get that V2 or V out is equal to, V1, we should solve for V1. V1 is equal to Vn minus V2. So we get that C1 over C2 times Vn minus V2 is equal to V2. So now we can distribute this and rearrange it and solve for V. So we get that V2 or V out is equal to C1 over C2 times V in minus C1 over C2 times V2. And so if we move V2 onto the same side and solve for V2, we get that V2 is equal to C1 over C2 times V in divided by 1 plus, divided by 1 plus C1 over C2. And so if we multiply this by C2 over C2 to cancel some of these fractions out, we get that V out here, or V2. So V out is equal to C1 over C1 plus C2 times V in. So notice that this looks, again, really similar to the format of the previous divider formulas that we came up with. And so this is for the, this is the voltage, or a voltage divider based on capacitors. But now notice that this is again the voltage drop across C2. So if you want the voltage drop across V1, so VC1 has to be equal to V in times C2 over C1 plus C2. Okay. Finally, we want to be able to analyze parallel capacitors. So for capacitors in parallel, we want the same configuration as resistors replaced with capacitors. So now it will look like just two capacitors in parallel branches like this. And we have an overall voltage across them and an overall current across them, and C1, C2. And we want this to be able to be represented through an equivalent capacitance, CEQ here. So CEQ with same voltage and current. And again, this is charging current. And from before, the same reasoning here, we get that. So we know that each of these will have a current through them. So I1 and I2. So this is I1 and I2. Sorry, let me rewrite this. I2. And we know I1, or total current, is equal to I1 plus I2. And since I is equal to Q over change in time, if we multiply both these by a time interval, we get that total charge is equal to charge on capacitor 1 plus the charge on capacitor 2. So this is different from series where they have the same charge. These are the sum of the charges is equal to total charge. And then we have here that the total charge here is just Q because we want this to be equal. So this total charge here, so we have, this is QEQ because this is the total charge across these two capacitors, and we want this capacitor to have the same total charge. And so from the equation, we know that since Q is equal to CV, we have Q or Q1 plus Q2 is equal to QEQ, substituting Q equals CV, we get C1 V1 plus C2 V2 is equal to CEQ VEQ. And now since the voltages are all equal, so V1 equals V2 is equal to VEQ, we get that, we can cancel these voltages out, and we get that C1 plus C2 is equal to CEQ. And generalizing this to multiple capacitors, we can get that CEQ is equal to the sum of parallel capacitances. So this is the general formula for capacitors in series. All right, now if we want to gain intuition for this, we can look at the capacitor formula or capacitance formula again, and C is equal to K epsilon naught area over distance. Again, now if we're adding capacitors in parallel like this, we can see that we are, you can think of it as increasing the cross-sectional area of the plates, because if you have these capacitors in parallel, then it's almost acting as if like the plates are, you're adding the areas from both of these plates as the area for this formula here. So since capacitance is directly proportional to area, you can think of equivalent capacitance as being the direct sum of these capacitors. And now one thing to know is that when you do have these two capacitors here in parallel, and you want to find the relationship of the charges between them, so like Q1 and Q2 for C1 and C2, notice that Q is equal to CV, and since voltage is constant, here we get that the charge is directly proportional to the capacitance. So Q1 over Q2 is equal to C1 over C2. So these are directly proportional. So because the voltage is the same across them. All right, so that is resistors and capacitors configurations.